Swayam Prabha. Digital India. Educated India.
Welcome to the 10th and the last lecture on the lecture series named Tutorials on Design of Transmission Elements. In this lecture, we will study about belt drives, and in the belt drives, we will take first a problem related to the belt, and thereafter we will take problem related to pulleys. So, first of all, let us review the belt drive. We have rigid versus flexible drives. The drives which we studied in our earlier classes, those drives were gear drive, and those drives are called the rigid drives. In this case, there will be a flexible member between the driving and driven shaft, and therefore, this drive or the belt drive is called the flexible drive. So, just review it. There are two types of drives, rigid and flexible. Gear drives are called rigid or non-flexible because the shaft, the driving shaft and the driven shaft are connected with the help of rigid members, the rigid driving gear and the rigid driven gear. So, there is direct contact between the driving and the driven shaft through the gears. In the flexible drives, there is an intermediate link such as belt, in this case is the belt, rope or chain between the driving and the driven shaft. So, on the driving shaft, a driver pulley will be mounted, and on the driven shaft, a driven pulley will be mounted, and these two pulleys are connected with the help of flexible member known as either belt, rope or chain. In the case of chain, in place of pulley, there will be sprockets. Since this link is flexible, the drive are called flexible drives. Now, let us take a problem related to selection of belt. So, it is required to select a flat belt drive for a compressor running at 720 RPM, which is driven by a 25 kilowatt 1440 RPM motor. It means the driven shaft is driven by a motor and the power is 25 kilowatt and the RPM of the driven shaft is 1440 and the driven shaft has RPM or the revolution equal to 720 revolution per minute, and the driven shaft has to run a compressor. Now, space is available for a center distance of 3 meters. The belt is open type. So, in this problem, we have this is the driving shaft here. This is the center of the driving shaft. This is the center of the driven shaft. And on the driving shaft, a driven pulley is mounted, driving pulley is mounted, and on the driven shaft, the driven pulley is mounted. And the center distance between the axis of rotation of the driving shaft and the driven shaft is given as 3 meter, and in mm it is 3000 mm. Now, the given information in the problem is the revolution of the driven one is this one, and so it is rotating with the speed of 720 RPM, and the driving shaft has to rotate with 1440 rpm. And so the velocity ratio between these is a velocity reduction equal to 1440 divided by 720, and which is equal to 2. So reduction of the speed is achieved by this drive equal to 2, and the power is 25 kilowatt, and the center distance is 3000 mm. Now, selection of flat belt from the manufacturer's catalog. In practice, the designer has to select a belt from the manufacturer's catalog, and for the selection of a proper belt for a given application, the following information is required. The first is power to be transmitted. In our case, it is given as 25 kilowatt. The input and output speeds. In our case, it is the input speed is 1440 rpm and the output is 720 rpm. The center distance depending upon the availability of the space. In our problem, it is given as 3 meter. Then the type of load which will act on it, and in the problem it is given that this belt drive is to drive a compressor. So this information is also given. So with these all information, now we will go for the selection step of the belt drive. Now the selection procedure is, the basic procedure for selection of flat belt consists of the following steps. Step 1 is the optimum belt velocity of Dunlop belts. There are number of manufacturers of the belt, and in this problem the Dunlop's belt is taken for the selection, and so the optimum belt velocity of Dunlop belts is from 17.8 meter per second to 22.9 meter per second, and this optimum velocity is equal to under root of the P maximum divided by 3m. Let belt velocity is selected as, within this range, it is selected as 18 meter per second in this range, and calculate the diameter of the smaller pulley by the following relationship. The diameter of the smaller pulley is equal to 60 multiplied by 1000 multiplied by this belt velocity divided by pi n, the revolution of the smaller pulley, where n is the input speed or rpm of the smaller pulley. The diameter of the bigger pulley is obtained from the velocity ratio given or the required. So in our problem, n1 is 1440 rpm and n2 is 720 rpm and the center distance is 3 meter. So the diameter of a smaller and bigger pulleys are given by this formula. This will give you the diameter of the smaller pulley. By substituting using belt velocity v is equal to 18 meter per second, the diameter of the smaller pulley is obtained from this formula. V will equal to 60,000 divided by pi n1. Now substituting V, which we have selected 18 meter per second, and n1, the speed of the driving pulley or the smaller pulley is 1440 rpm. We got the smaller pulley diameter as 238.73 mm. Now selecting the preferred pulley diameter of 250. This preferred pulley diameter is selected from the manufacturer's table, where a list of preferred pulley dimensions are given. Now if we are selecting 250, then the diameter of bigger pulley will equal to velocity ratio multiplied by diameter of the smaller pulley. Now the pulley diameter selection is based on the preferred diameters of cast iron and mild steel pulleys, and the preferred pulley diameters are given in this row. That means you may select 100, 112, 125, 140. From our calculation, we have obtained the smaller pulley diameter as 238.73. So, in this given information, near to this 238.73 mm is the diameter equal to this 250, near to this one, because 224 will become quite smaller in comparison to this, and 280 will be quite bigger, and so the preferred number which we will select is 250, and the bigger diameter is selected by a smaller diameter multiplied by speed of the smaller pulley and speed of the bigger pulley. Now, a smaller pulley is selected as 250 mm and speed of the smaller pulley is 1440 and speed of the bigger pulley is 720, which is equal to 2. So, from this relationship we will get the diameter of the bigger pulley. So, diameter of the bigger pulley is obtained as 500 because this is equal to 2. So, we got the diameter of the smaller pulley and the diameter of the bigger pulley. Now, modify the values of d diameter of the smaller pulley and diameter of the bigger pulley to the nearest preferred diameters if required. But in our case, the small d is 250, which was selected from the preferred pulley diameters given, and the diameter of the bigger pulley is obtained as 250 multiplied by 2, and that is 500, and this 500 is also there in the preferred diameter series. Now, determine the correct belt velocity for these preferred pulley diameters and check whether the actual velocity is in the range of optimum belt velocity or not. Now, belt velocity for these dimensions is given by the diameter of the pulley which we have selected is 250. So, with this small pulley diameter, now we will find the velocity of the belt, which is equal to pi d n1 divided by 60 multiplied by 1000. We are dividing it by 1000 because d is taken in mm, and the velocity is unit is meter per second. So, by substituting the selected small pulley diameter as 250, we got the belt velocity equal to 18.85 meter per second. And in the first step, we have seen that the preferred range of the belt speed for the Dunlop is 17.8 to 22.9. So, the obtained belt velocity will be checked whether it is coming within this range or not. So, it is 18.85 which is coming in the range, because the optimum belt velocity of Dunlop belts is from 17.8 to 22.9, and the calculated value of V is lying in between this. It means the pulley which we have selected is providing the optimum belt speed or the velocity. So, it is in the range of optimum belt velocity. Now, the step 2. Determine the load correction factor FA from table upon the type of load. Find out the maximum power for the purpose of belt selection by following relationship. That means the power which you want to transmit, the maximum one is equal to FA, the load correction factor, multiplied by the power which you want to transmit. The power which we want to transmit is given in the problem. It will be multiplied by this load correction factor to get the maximum power which we can transmit. So, load correction factor FA is given by this table. Now, we have to drive a compressor. In the problem, it was given that we want to drive a compressor. So, for the compressor, the value of FA is 1.3. Okay. So, this 1.3 will be used to multiply the power which we want to transmit and which is given in the problem to get the maximum power. So, load correction factor is 1.3, and so K power maximum is equal to Fa multiplied by K. The kilowatt which we want to transmit is 25, and so the maximum power which we can transmit is 32.5 kilowatt. Now, selection of flat belt from the manufacturer's catalog, and that is the next step. The power transmitting capacities of the belt are developed for 180 degree of arc of contact alpha s. That means the maximum power which we can transmit, which we calculated just now, is based on the angle of wrap. This is the angle of wrap. That means if we take the driving pulley as this one, then the belt which touches the surface of the driving pulley is from this end to this one, and thereafter from this dot it leaves the surface of the driving pulley, and at this dot it leaves the surface of the driving pulley. So, the wrap angle of the belt is given by this angle. It is given by alpha s. Alpha s. For the driving pulley, for the driven pulley, this angle is this one, because the belt is leaving the surface of the driving pulley at C and E. So, this bigger angle is the angle of wrap, alpha b for the case of driven pulley. Now, the power transmitting capacities of the belt drive are developed for 180 degree of arc of contact alpha s of the driving pulley. The actual arc of contact will be different in different applications. In the case of open belt, we see that this angle of wrap is lesser than 180. 180 angle is this one. This is 180. So, our alpha s is lesser than 180. When the arc of contact is less than 180, as is the case here, there will be additional tension in the belt, to account for which a factor called arc of contact factor is used in calculations. So, alpha s is given by the angle of wrap of the driving pulley is given by 180 minus 2 sine inverse. Capital D is the diameter of the outside diameter of the driven pulley minus small d, which is the outside diameter of the driving pulley, divided by 2c, where c is the center distance, center of rotation of the driving shaft and the center of rotation of the driven shaft. And the alpha b, that means angle of wrap of the driven pulley, is given by 180 plus 2 sine inverse capital D minus small d divided by 2c. Now, calculate the angle of wrap for the smaller pulley by the following relation. Find out the arc of contact factor Fd from table based on our alphas. In the given problem, we will select the value of Fd. Now, it is not advisable to use an arc of contact less than 150 degree for the flat belt drive. Therefore, the minimum arc of contact should be 150 degree. Now, let us find for our case what is the value of alpha s. The maximum power which we can transmit when the alpha s is 180 degree is given by 32.5 kilowatt, and we want to correct it based on our angle of wrap alpha s. So, alpha s, by substituting the value of capital D and small d is obtained as, capital D is the diameter of the bigger pulley and we have obtained it as 500 mm, and the small d is the pitch circle diameter of the smaller pulley and we have obtained is as 250, and the C center distance is given in the problem as 3 meter or 3000 mm. So, by substituting all these values we get alpha s is, or the angle of wrap of the smaller pulley is 175.23. It is more than 150. It is more than 150, and so it is correct, because alpha s should not be less than 150 degree for the case of flat belt. Now, based on this alpha, we have to find this correction factor, arc correction factor FD. Our alpha s is 175, which is lying between this alpha s, the alpha s is equal to 170 and alpha s is equal to 180. So, we will do the interpolation to get the value of FD for 175.23 alpha s, which is lying between these two. So, that interpolation is done. Assuming linear interpolation, the arc of contact factor is given by, we have done the linear interpolation between the two values. For the case of 180 degree arc angle, correction factor FD is 1.00, and for 170 degree is 1.04. So, by interpolation we got FD as 1.019. So, corrected power is now FD multiplied by kilowatt maximum, which we have obtained in the previous step. So, 1.019 multiplied by this 32.5 is equal to 33.12 kilowatt, which is to be transmitted. Now, step 5th, there are two varieties of Dunlop transmission belts, high speed duck belting and Ford duck belting. High speed duck belting is used in general purpose applications, and Ford duck belting is recommended for heavy duty applications. The range of optimum belt velocity for these two belts is 17.8 to 22.9. The power transmitting capacities of the belts are as follows. For the high speed, it is 0.0118 kilowatt per mm width per ply. We will see what is the meaning of this ply. And for the Ford belt, it is 0.0147 kilowatt per mm width of the belt. Belt has some width and it has number of plies. So, based on that, the power transmitting capacities are given. The meaning of this 0.0118 means it can transmit 0.0118 kilowatt if the width of the belt is 1 mm and the number of ply is 1. So, the above values are based on the following assumptions. The arc of contact is 180, the belt velocity is 5.08 meter per second. There is a specific term, power rating or load rating of flat belts. The power rating of flat belt is defined as the power transmitting capacity of the belt per mm width per ply at 180 arc of contact. So, in the previous step, we have obtained the power transmitting capacity as 33.12 by multiplying the maximum power capacity by FD, which is the arc correction factor. So, now what we will do is, now we will find the corrected kilowatt rating knowing the capability of the belt. Either if we can select the high speed belt or the Ford belt. Now, we are selecting the high speed belt, and so the corrected kilowatt rating will be given by this formula. And this formula is based on the belt speed. Okay, so the selecting a high speed belt, the corrected rating at a belt speed of 18.85 belt speed was obtained in the previous step. So based on that, the corrected belt rating is this. In this formula we will substitute the value of V, and so it is equal to 0.0438 kilowatt. The power rating of fourth belt is 0.0438 kilowatt. It indicates that a single ply fourth belt of 1 mm width will transmit 0.0438 kilowatt power for 180 arc of contact with the pulley. Again, the arc of contact is taken as 180 degree while defining the maximum power capability of these two types of belts. Then the belt construction. Here we will study about the term ply. There is a specific term ply of the belt. In order to make a practical thick belt, the layer of the belt material are cemented together as shown in figure A. The one layer of the belt is cemented to another layer, and this is cemented to again another layer, and so the layers are 1, 2, 3, 4, and so it will be called 4-ply leather belt. The belts are in the fabric type also, where the fabric is oriented either in this way or in this way or in this way, and in between these fabrics a filler binding material will be used. Now these layers are called the plies of belt. Belts are specified according to the number of layers or plies, for example single ply, double ply or triple ply, and so the power transmitting capability of belt which we have determined was based on per unit width of the belt when this width is 1 mm and when number of ply is 1. So per ply and per unit width of the belt, that was the power transmitting capability of the selected belt. The power rating of the belt is also specified per ply of belt. For example, the power rating of Dunlop high speed belt is 0.0118 kilowatt per ply per mm width of the belt, which we have seen in the previous slide. Now, in the next step, calculate the product of width multiplied by number of plies by dividing the corrected power by the corrected kilowatt rating, or width multiplied by number of plies is given by corrected power divided by corrected belt rating. That means kilowatt corrected and the corrected kilowatt rating of the belt. Now calculate the belt width by assuming a suitable number of plies. In this step, there are a number of alternative solutions. A belt whose width is near the value of the standard width is the optimum solution. For this belt, select the standard belt width. The corrected power rating obtained in the previous step was this 33.12 kilowatt. Now from step 5th, the corrected power rating of belt was obtained as corrected belt rating 0.0438 kilowatt. Then in this step, we will selection of belt. So this rating is per unit width per unit ply, and the power which you want to transmit is 33 kilowatt. Okay, so the width multiplied by number of ply which we require is given by the power which you want to transmit divided by the power transmitting capability per unit width per unit ply. So it is this 33.12 divided by the corrected belt rating, which is 0.038, and it comes as 756.17. It means the multiplication of width of the belt and number of plies should be 756.17. Now, selection of belt width. The standard widths of these belts are as follows. For the 3 ply, the widths are 25, 40, this. For 4 ply, this one. For 5 ply, these are the belt widths. For 6 ply, these are the belt widths. So, from the previous step, we have obtained that width multiplied by number of plies is equal to 756.17. Now, let us find the width. If we are selecting 4 ply, then the width will equal to this 756 divided by number of plies. And number of plies, if we are selecting 4, then width will equal to 756.17 divided by 4. It means the width should be 189.404. Now, for 4 ply, the standard widths are up to 152 mm and the required one is 189.04. It means this 4 ply is not satisfying our requirement. Now, we are coming to the 5 ply belt, in which there are 5 layers. 5 layers, 1, 2, 3, 4 and 5. So, this width will equal to this 756.17 divided by 5, because now 5 is the number of plies. So, it comes as 151.23. So, when we see the standard table, then for 5 ply, the width of the belt is up to 152 mm and the requirement is 151.23. It means we may go for the 5 ply and the width may be taken as 152. But let us see for the 6th ply also. For the case of 6 ply, the width is this divided by 6 and it comes as 126.03 mm. Now, for the 6 ply, the standard widths available are your 112, 125, 152, 180 and 200. So, we may go for this 152. So, in both the cases, we are having 152. So, why not take this 5 ply? So, we are selecting 5 ply and the width will be taken as 152. So, we shall select a high speed belt of 152 mm preferred width and 5 plies. Now, the relationship between belt and pulley widths. This table provides us with belt width from 125 up to and including 250, the pulley to be wider than belt width by 25 mm. Now, our belt width is 152, which is lying between this range, and so the pulley width should be more than 25 of the belt width. And so, the pulley width is obtained as 152 plus 25 and so 177 mm. Now, the length of the belt. Now, calculate the belt length by using the following relationship. The belt length is given by this one in terms of the center distance and the bigger pulley diameter is smaller pulley diameter. Substituting these values, we got the length of the belt as 7183.31 mm. Now, minimum pulley diameters for given belt speed and belt plies. The belt velocity obtained is 18.85 and the diameter of the smaller pulley is 250 and the bigger pulley is 500. Now, this table suggests us for the number of plies what should be and for the maximum belt speed what should be the pulley diameters. In our case, the pulley is, we have selected a high speed belt of 152 mm preferred width and 5 plies. Therefore, the minimum pulley diameter will be 240 and so our minimum pulley diameter will be in between this and this, and by interpolation you can obtain, and it will be between 224 and 250, and in our case the pulley diameter is 250 mm, which is more than the minimum allowed diameter of 240 mm. Therefore, it was a right selection. Now, let's see the second problem, which is related to the pulley. A pulley made of grey cast iron, FG 150. FG 150 is the grade of the cast iron, where 150 represents the ultimate tensile strength of the material of the pulley, and that means the cast iron. It transmits 10 kilowatt of power at 720 RPM. The diameter of the pulley is 500. The pulley has 4 arms, 1, 2, 3, 4 arms of elliptical cross section. The cross section of the pulley is shown as the ellipse. The elliptical cross section is there, in which the major axis is twice of the minor axis. The major axis of the cross section is this one, and the minor axis is given by this. The minor axis is small a and the major axis is small b. So, in the problem it is given that b is 2 times a. Now, we have to determine the dimensions of the cross section of the arm, if the factor of safety is 5. Let's start the problem. There are 3 important things about the arms of the pulley. They are as follows. The arms of the pulley have elliptical cross section. The major axis of the elliptical cross section is in the plane of the rotation. The major axis of elliptical cross section is usually twice the minor axis, and it is given in our problem also. Elliptical cross section reduces aerodynamic losses during the rotation of pulley as compared with rectangular cross section. Therefore, invariably the arms have elliptical cross section. Now, material of the pulley is grey cast iron. It is FG 150, and so ultimate tensile strength will be 150 megapascal. And these are the other values given. The b, small b, the major axis of the cross section is equal to 2 times the minor axis. Then the permissible stress will be the ultimate strength of the material of the pulley, which is FG 150 with ultimate tensile strength 150, and the factor of safety is given in the problem as 5. And so, the permissible stress which you can apply on this arm is 30 Newton per mm square or 30 megapascal. The bending moment on arm. The torque transmitted by pulley is given by this formula, and you see this formula is obtained as the design of these arms illustrates the application of simple formula for bending stress. That means, you see, the load will act at this end, and at this end the bending stresses will act. So, this principle is used here. It is assumed that the half of the load will be shared by the belt. That means, you see, if number of arms are n, then due to this wrap, this n by 2 arms will bear the load of transmission. So, it is assumed that the belt wraps around the rim of the pulley through approximately 180 degree, and half of the arms carry the load at any moment. This is illustrated in figure below. The torque transmitted by the pulley is given by the torque the pulley may transmit will equal to this P multiplied by R will be the moment multiplied by N divided by 2. Okay. And so, the load, this P which will act on the arm is given by 2 the torque which is to be transmitted divided by radius of the pulley multiplied by number of arms. So, let us use this formula. The bending moment acting on the arm is given by simply this is the root of the arm, and at this end load P is acting, calculated by this formula, and the bending moment will be equal to P multiplied by R, and the bending from A and B, this bending moment MB is equal to the torque which we want to transmit divided by number of arms. The major axis of the elliptical cross section is in the plane of rotation. So this is the correct way, this is not the correct way, because in this way we will get the y distance of the bending stress equation. Sigma is equal to my by I. In this case, we will get this y. For this elliptical cross section with A and B as minor and major axes respectively, I is given by I of this elliptical cross section is given by pi a b cube divided by 64. This I is bigger, and so sigma will be smaller for this case. So since the major axis is twice of the minor axis, the I is given by pi a to the power 4 divided by 8 and y is equal to b divided by 2, which is equal to a. And the bending moment, by substituting the value of I and the mb and y, is obtained as this formula, and solving this for a, we got the dimension of the cross section of the arm of the pulley, and it comes as 1.72 cube root of mt divided by number of arms multiplied by sigma b, the bending stress. So P is obtained as, by substituting mt is equal to this one, and r, the radius of the pulley, n is 4, and so P, the load which will act, is equal to 256.26. So the bending moment is equal to P multiplied by R. So this bending moment is acting on the arm. So cross section of the arm, for elliptical cross section, I is obtained as this, and substituting B is equal to 2A, the I is A pi to the pi a to the power 4 divided by 8 mm to the power 4. So the bending stress, the allowable stress, is equal to the ultimate tensile strength divided by factor of safety, and which is 30 megapascal. Substituting the value of mb, y and I, we get the A, the minor axis of the cross section of the arm of the pulley, and it is 17.78. We selected it as 20 mm. Then B is equal to 2 times A, which is 40 mm. Alternatively, using below equation, we can get the value of A, and the A comes as again 17.78 or 20 mm. Now let's take the third problem, again related to the pulley, but here our aim is to determine this dimension. So the third problem is, a belt pulley made of grey cast iron FG 150 has 4 arms of elliptical cross section in which the major axis is twice of the minor axis. The tensions on the tight and slack sides of the belt are 750 and 250 Newton respectively. The mean diameter of the pulley is 300 mm, while the hub diameter is 60 mm. Determine the dimensions of the cross section of the pulley arm near the hub. Near the hub, the cross section is required. Assume that half the number of arms transmit torque at any time. The factor of safety is taken as 5. So this is the cast iron pulley. The cross section is elliptical, and the same will be at the root. So there are 3 important things about the arms of the pulley. They are as follows. This we studied in the previous problem also, and thus I am not repeating it. Okay, the same formulas are used. Directly I am coming to this point. So material of the pulley is grey cast iron FG 150, and the tension on the tight and slack side is 750 Newton. This P1 is 750 Newton and P2 is 250 Newton. And the diameter of the pulley is 300 mm. And the hub diameter means this. Hub diameter is equal to 60 mm. It is given in your problem. Now SUT is 150 because the material is FG 150. So SUT will be 150 megapascal, and factor of safety is 5. Number of arms is 4, and the elliptical cross section has A equal to half of the B. So permissible stress again is 30 megapascal. Bending moment on arm as shown in figure, this bending moment is MT is P1 minus P2 multiplied by capital D divided by 2. So that will be the bending arm, and substituting P1 and P2 and D, we obtain the torque which will act on these is equal to 75,000 Newton mm. So this torque is actually MT, and this is equal to this value. Now, assuming that one half of the arms carry the load at any time, the tangential force P at the end of the arm is given by this equation, and so the P which is acting at the ends of the arm is equal to 2 times the torque which is to be transmitted, MT, divided by Rn. R is the radius and N is the number of arms. So it comes as P. So P equal to 250 Newton will act on the arm, and this arm will be under bending. The arm length L for the bending moment at the section XX near the hub is given by, near the hub, this is the section of the arm, okay. The length L, the length of the arm is given by capital D divided by 2 minus small d, the hub diameter. So this distance is the half of the hub diameter, small d divided by 2, and this is capital D divided by 2. This capital D divided by 2. And so the length of the arm up to this XX section will be capital D divided by 2 minus small d divided by 2. It is 120 mm. So the length of the arm on which the load P, this P will be acting, is L, and from that we will get the bending moment. So at section XX, the bending moment is this P which is acting on the arm, the P multiplied by L. L is 120 and P is 250 Newton. So 250 multiplied by 120, this much of bending moment is acting here. So this bending moment will be used to determine the cross section. So in the problem given that the cross section B, the major axis, is twice the minor axis. So the second moment of area of this elliptical area about this axis, neutral axis, is given by pi a to the power divided by 8, and the y, the bending moment as we see, is proportional to the distance from the neutral axis. So y at any section will equal to b divided by 2, and it will be equal to a, the length of the minor axis. So the bending moment we know that is equal to my divided by y, where m is the bending moment which acts at that section. So bending allowable stress is 30. Substituting MB, y is equal to a and I in terms of a, we will get the value of a, and a is 13.66, or rounding off we took it as 15 mm. And so the B at XX section, means this section, is equal to 30 mm. Then the crowning of the pulley. Pulleys are crowned so that the belt remains in the middle of the pulley. So objective of providing pulley crown are as follows. The crown on the pulley helps to hold the belt on the pulley in running condition. The crown on the pulley prevents the belt from running off the pulley. The crown on the pulley brings the belt to running equilibrium position near the mid plane of the pulley. Now, based on the pulley diameter, the crowning height is decided. Now, as pulley diameter in our case is 300 mm, which is lying between this one, 300 mm. Okay, so this range we have H is selected as 0.8 because the range for this range is 0.8, and then starts the range from 315 to 355. And so for our case, when the pulley diameter is 300 mm, we have taken it as 0.8. And so this will be, then cast iron pulleys are made of grey cast iron, Fg 200. The proportion of these pulleys are given in the figure like this. Number of arms for pulleys up to 200 mm diameter, use web. For pulleys 200 mm diameter to 450 mm diameter, 4 arms. For pulleys above 450 mm diameter, use 6 arms. As the pulley diameter is 300 mm, so the number of arms should be 4, and in the problem it was given 4 also. Now, the cross section of arms pulley, this cross section may also be obtained directly from this formula, where thickness of the arm be near boss. That means at this XX section which we determined for the single belt and for the double belt, where A is the width of the pulley, capital D is the diameter of the pulley, and small n is the number of arms in the pulley. So, you can use this formula also to get the thickness of the arm near the boss. This is the boss. So, near it, the thickness B, this B can be determined from this one. In our case, number of arms is 4, the diameter of the pulley is 300, and the width of the pulley can be determined knowing the width of the belt, which we studied in our first problem. So, knowing the width of the belt, you can find width of the pulley from the table which says what should be the width of the pulley. This table, width of the pulley. Pulley to be wider than belt width by mm. So, knowing the width of the belt, you can find the belt width of the pulley. And so, the width of the pulley A will be here, and you can find the value of A. Now, thickness of the arm B1 near rim. Thickness of the arm B1. Where is B1? See this one. Near the rim, what would be the thickness? And this thickness, use taper 4 mm per 100 mm from the boss. It means once you have obtained thickness B near the boss, using taper 4 mm per 100 mm, you can find the thickness of the arm near the rim B1. Then radius of the cross section of arms. That means, what see in this figure where this R, small r is at this location. Okay. So, radius of the cross section of arms R is equal to 3 by 4 B, and minimum length of the bore L. That means this is the bore or hub, you may say, not bore. Near the bore, this is actually bore, and this is showing the keyway. Okay, so this length L is given by 2 by 3 of the A. Okay, it may be more for loose pulleys, but in no case it should exceed A. Now, what is A? A is this one, width of the pulley. Knowing the width of the pulley, you can find what would be the length near the bore. Now, another condition is D1 minus D2. D1 is this distance, D1 minus D2. D2 is this one. That means diameter of the shaft on which this pulley is mounted is D2. D2 is the diameter of the shaft on which the pulley is mounted. So, D1 minus D2 divided by 2 is equal to 0.412 multiplied by cubic root A, the width of the pulley, multiplied by capital D. Capital D is the outside diameter of the pulley considering the crowning, plus 6 mm for single belt, and D1 minus D2 divided by 2 is equal to 0.529 multiplied by cubic root of AD plus 6 mm for double belt. Now, radius R1 and R2. R1 is the fillet radius at this location, and R2 is the fillet radius at this location. These two are given as B divided by 2, where B is the major axis. In this diagram, it is the minor axis is B divided by 2, and so the major axis of the cross section of the arm is B. So, knowing this B, the R1 can be determined is equal to B divided by 2, and R2, this fillet radius, is equal to again B divided by 2. Now, thickness of rim. What should be the thickness of the rim? This one. It is equal to capital D, the rim diameter, divided by 200 plus 3 mm for single belt, and it is equal to capital D divided by 200 plus 6 mm for double belt. In our case, it is the single belt. So, we will divide the rim diameter by 200 and we will add it 3 to get the value of T. Now, these are the references which were used in this particular tutorial, but basically the last reference, which is Design of Machine Element by V.B. Bhandari of Tata McGraw-Hill, was used in this tutorial, and the problems which were taken in this tutorial class were from the last reference. So, this is all about the design of belt drives. In this design of belt drive, we studied the way by which belt is selected from the manufacturer's catalog. The number of steps were used by taking a problem. Thereafter, we studied the dimensions of the cast iron pulley, and we took two problems. In the first problem, we studied the way the cross section of arm is determined, and cross section of arm is elliptical with the major axis equal to twice of the minor axis. So, we determined the cross section of the arm, and thereafter we also studied the cross section of the arm near the boss. So, that is all about this lecture series. This was the last lecture. Thank you.